Good evening and welcome to our second event in our 2024 Public Speaker Series, The Journey of Australian Science, Tracing Our History and Discovering New Paths. I am Professor Susanne von Caemmerer, and I'm a Fellow of this Academy and one of the conveners of the series, along with Dr. Oliver Mayo and Associate Professor Raffaella Demichelis. Tonight, we're on Ngunnawal country, and I would like to acknowledge and pay respect to the traditional owners of the land, as well as all the lands on which our online audience may be joining us from. As we share our knowledge, teaching, learning, and research practices, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. Thank you for being here at the Shine Dome tonight, and thank you to those joining us online. Tonight, we will focus on the world of soil science and the work of Professor James Arthur Prescott, who was an Academy Founding Fellow in 1954. Professor Prescott was not only a scientist concerned with fundamental research, but a conservation-minded agriculturalist. He recognized the need for land development in Australia, provided it was based on sound principles and attempted within the limits imposed by climatic conditions. His classification and mapping of Australian soils and his direction of detailed soil surveys of strategically chosen areas, together with his climatological techniques for determining the availability of soil moisture, provided the best practice parameters for the use and conservation of Australian soils. Our two speakers tonight will explore the early contributions of Professor Prescott in soil science, and they will share their work and what we can expect for the future. But before we hear our speakers, if you would like to join the conversation on social media, do so by using the hashtag ScienceJourney. Questions from the online audience can be submitted by scanning the QR code that will appear on your screen during the event. And questions from the audience in the Shine Dome can be asked at the microphone during the Q&A session at the end. So now let's hear from our first speaker, Professor Brajesh Singh. Brajesh is a world-leading soil ecologist. He's currently based at Hawkesbury Institute for the Environment at Western Sydney University, and he was elected last year as a Fellow of the Australian Academy of Science, and he's best known for his studies that demonstrate the central role of soil microbes in predicting, mitigating, and adapting to climate change. Please come up and share.
Thank you very much, Susanne, for a very, very kind introduction, and good evening, everybody. May I start with saying that it is an honor and privilege to stand here in front of you and talk at the event that is celebrating the legacy and the journey of Professor James Prescott. What an extraordinary journey and impact Professor Prescott had on soil science in Australia and globally. I obviously was very well aware of his science, but recently I got opportunity to look at his biography, the journey of his early career. What a fantastic career he had. He has started his scientific career in UK, moved then to Egypt, then but come back UK, and then finally decided to come to Australia, where he established and led multiple national initiatives. In my opinion, he had a transformational impact on transformational impact on many aspects of the soil science across the globe. Particularly in the mapping, which we will say today that's one of the core activities of mine, so I've learned a lot from his science. Multidisciplinary approaches, soil-plant nutrient interactions, which are still, some of them are still being used for the policy and the management actions. Professor Prescott then decided to go abroad. He went to India and then to Thailand, and working on a very, very different topic, and that it was a laterite science. So the breadth and the depth of his work is just phenomenal. And I have no hesitation in saying that seems like unparalleled and unmatched in the soil science. I'm I would like to start with saying thank you very much to Australian Academy of Science to celebrate the legacy and the impact of Professor Prescott. But I would also like to acknowledge the Soil Science of Australia, which has been celebrating the contribution of Professor Prescott since 1971, when they established a medal on his name, J.A. Prescott's Medal of the Soil Science, that is given annually to outstanding contribution in the research in the soil science. That's how it looks like. I have got a copy of the replica here, the original here. This is Soil Science Australia brought very proudly to show you. And I'm one of the proud recipients. I think that was 1921 when I was elected for this medal. So thank you very much, Soil Science Australia. I know many officials and the members of the Soil Science Australia in the audience today. So thank you very much for keeping and celebrating the Prescott legacy and impact on soil science. Professor, one of the things I want to take this discussion further from the Professor Prescott is that his research has always been multidisciplinary and always focused on the research approaches that impact the societal impact, so either the policy or the management actions. Keeping that in mind, I am going to talk today is how the healthy soil is the foundation of healthy society and healthy planet. If I have to say in one word, there's no terrestrial life is possible without healthy and functioning soils. That's how important each soil is. This is a paper from the copy taker just recently published. And in a very simple diagram, what it shows you that human health is not only the food and nutrients we get from the soils that's important, but it's also the majority of the medicines, or at least antibiotics, comes from the soil. But it's also the home of a small numbers in terms of the dominance, but a home of many human pathogens. Those have a direct impact on our health as a human society. On the planetary science point of view, almost all terrestrial planetary functions is dependent on the functioning of the healthy soils. For example, primary productivity, nutrient cycling, water cycling, and habitat for the biodiversity. I will talk about that one by one as I progress through these discussions. But just for a reminder, a recent analysis by the United Nations Food and Agriculture Organization found that healthy soils is a prerequisite to achieve almost all SDG. That's how important is healthy soil for the human societies and human survival. But what is healthy soils? That's just like human health. There is a lot of definitions of healthy soils. I'm not going to go in that debate today, but I want to say that the healthy soils are the living systems that provides planetary functions that keep the terrestrial ecosystem working. That's how it's the core of survival of the terrestrial ecosystems. It has three components: physical, chemical, and biological, all interact together to ultimately affect the soil health. In today's discussions, I'm mainly going to focus on the biological side of health for two reasons. One reason, I've recently spoken at one of the ECOLA events on the soil carbon and its critical role in the food productions and climate mitigations. But also the soil biology is the core of my own work. But I would say that up front, will be the soil chemist and physicist here, that every component of soil biology is important. And ultimately, they interact with each other to affect the soil health and soil functions. And if you have a healthy soil biology, you will have healthy soil physics. If you have a healthy soil physics, you will have a healthy soil chemistry. So it is interconnected. But the focus of the today discussions is soil biology. Just getting back to how important it is for the human ecosystem services and planetary health, 95% of our calorie intake still come from the soil. So with all the technological advancements, 95% of our caloric intakes still come from the soils, crop productions. This is quite well known. There's less known aspects of the planetary functions is the critical role that soil and soil health play in buffering and filtering of the water systems that have huge impact on the quality of the running and the groundwater. And the critical role soil plays in the climate regulations through the emissions and the mitigations of the greenhouse gas greenhouse gas. I'll come to that in a minute. One of the reasons I'm going to focus here on the soil biota, these functions are carried out by the soil biota. That does not mean soil physics and chemistry does not have impact. It does. But the functions is carried out by the soil biota. The concept of the soil health and the soil biology is not new. If you look at the oldest human literatures, they are always mentioned about, in fact, most of the human civilization have started and fallen on the quality of the soils. This is just one, when the Caemmerer was the queen of the Egypt, the removal of the earthworm was punishable by death because they thought that by doing that, you will offend the god of fertility. That will result in the failure of crop, and if the failure of crop means famine, war, and all social strife. So the concept and the importance is well recognized throughout the human civilization. And why this is well recognized? Just is taken one example of the biodiversity. Soil is the home of the majority of the biodiversity on planet Earth. 59% of global biodiversity lives inside the soil. That's how important it is. And not only that, the activities of these 59% of organisms that ultimately also create the niche and habitats for above ground biodiversity, that's the trees and the animals. So they are a critical component of biodiversity and supporting the overall biodiversity of the health. I said I will talk about very briefly about the climate regulations. Soils have a huge impact how our climate looks like. At this moment, the atmospheric carbon dioxide is around 800 billion tons. And we probably emit through the fossil fuels and land use change around 9 to 10 billion tons annually. That increases the concentrations that are driving our climate change. Plant stores around 550 billion tons of carbon, its biomass. Soil alone contains more than 2,000 billion tons of carbon. And think about that, if you lose even the 25% of this carbon from the soil, what impact it will have on our climate. It will be almost inhabitable, definitely inhabitable for humans, but inhabitable for many other organisms on the planet. And these carbons are directly dependent on keeping the soil healthy and biodiversity intact. But the crop and role in the crop productions and the climate regulation is well known. Today I'm going to focus a little bit more about the human health and the plant health side of the things in today's discussions. There's never a day goes without in the TV or the magazines or the newspapers we don't talk about how important is the human microbiome in our health, not only digestion and nutrition, but our immune system, our physiology, our social behavior, our mental health, our reproductive success. Almost every aspect of human is greatly and significantly influenced by the microbiome we host in our gut, in our skin, in our mouth, in our reproductive organs. Plant is not any different. In fact, I will argue plant is even more dependent on its microbiome and its soils that provide the microbiome to it than animals and humans. Because if the condition is really harsh, animals, including humans, can move away from that areas. Plant can't. Plant are sessile and they're dependent on adjusting their own physiology and the microbiome it hosts to get survive that stress conditions. And what is the source of that microbiome? Soil. Healthy soils. And 85% of the microbes that are colonize plant roots and the plant body are originated from the soils. So healthy soils provide the seed, and a significant number of human in our own body originates from the soils and that soil from the soils. On that basis, we argued, and successfully argued, that the soil health and soil microbiome must be explicitly included in one health policy of the World WHO, the World Health Organizations. Because we as humans get a direct beneficial microbes from the soils. The soil surrounds us. But we also get it indirectly through the plant. Plant 85–90% microbes comes from the soil that is ingrown, and through that, through the food, we get in our own body, or in other cases, through the animals. But that's a beneficial microbes. But the soil is also host of the pathogens, deadly pathogens. I will talk about that in a minute. And antibiotic-resistant genes. That's then transferred into the food in our body. That can have really, really negative impact. So unless we addresses the soil health and the soil microbiome, we are not addressing soil health as one health policy properly. I said I will talk about human health and pathogen impact. Significant number of pathogens lives in the soils. Anthrax, polios, E. coli, salmonella, listeria, you name all those deadly pathogens, they live in the soils. And we have recently done, again, this is just a time to recognize the contributions of the mapping that Professor Prescott has, I guess, put in his own work. We use the similar sort of mapping. So we sample across the globe and then map the distributions of multiple human pathogens. I'm just putting one example here, is Aspergillus. Aspergillus is in fact saprophytic fungi, but it is a opportunistic pathogens. It kills almost 2 billion people, 1.8 million among the immunocompromised peoples annually. So it's a deadly infections. And so we were looking at how there's a distribution across the globe. And those red are the high distributions, blue are the less distributions. What more important is that, what we found, that where the soil is healthy and soil biodiversity high, you have a less populations of the human pathogens, the dominance of the human pathogen. Same is true also for the antibiotic-resistant genes, and that has been, in fact, done a lot more research than the human pathogen itself. So that was human pathogens. Just take back over the plant pathogen. In fact, some level, plant pathogens had a more impact on the human society in many cases. For example, I'll argue there's not have been human era in human civilization history that their major disease outbreak has not happened and famine was not caused. This is on the bottom of the sea. You'll see there's an example of the Irish famine in 19th century that kills more than 1 million people and force 1 million people to move out of the Ireland by infection by one pathogen called Phytophthora infestans of the potato. So we have been looking at the distribution across the globe. This is again the mapping, looking at that. Again, the critical component, I want to look at that. Where you have healthy soils that supports healthy biodiversity, you have lower proportions of both the human and the plant pathogens. Simple rule, they occupy more diverse, they occupy more niche, and they push out the pathogens from the systems. And as a result, you have a less pathogens, less disease incidence, and less impact on the public health and the food securities. The worst news is this is only going to get worse. All the climate model, again, this Prescott approach, bringing ecology and soil science and climatology together. We've done a lot of modeling sort of things, not only us, there's a group in the UK, very similar results. What we're saying, that what this modeling suggests is that as the climate warms, most of those, both human and plant pathogens, will become more dominant across the globe. That will mean more disease incidence, more crop losses, more impact, negative impact on human health, unless we find solutions going forward. But these are obviously challenges. But even if you are looking for the solutions also lies in healthy soils and the microbes it holds. We recently proposed a new concept that in short and medium term, and when I say short and medium term, I'm talking about some decades to centuries. And when I talk about long term, I'm talking about millennia here. Because the rate of climate change is so fast, for the plant and the higher animals to adapt and acquire evolutionary traits to cope with that changes will take millennia. But microbes can do in weeks and months just because they reproduce fast, they replicate fast. So they acquire their character and then they provide that functions to each host, to the plant and to the animals. And there is a growing evidence, experimental evidence for this concept. Given the importance, and despite the central role of soil biodiversity in ecosystem function and service, soil biodiversity rarely appeared in the conservation policy discussions until recently. I'll talk about that in a minute. And the ignorance have been because it is too diverse. It is diverse. It is too diverse. So if you lose some, how this is going to make any impact? Can't see, can't describe. They are in the soils. We can't see some of them. We can't see it because they are microscopic. Some of microbes we can't describe. That's also true. Then what to protect and how to protect? And we have been trying to address this for last old decades, along with others. It's obviously not just us. Other people have been looking at that as well. But we have a focus on this area to look at how the soil biodiversity, that's in bacteria, fungi, viruses, protists, beneficials and harmful animals distributed across the globe. And we're not only looking at how they are distributed, we're also looking at where the biodiversity hotspots in terms of soil biodiversity, but also in terms of the ecosystem service they provided. And the idea is that when you provide that sort of information, then the policymakers can prioritize these areas for conservations and the protections policies. Where does the policy lie at this moment? Policy, I will argue, and I'm sure people will, I'm not saying that before 2030 nothing happened, but in my opinion at least, where the policy started moving in the direction was 2013 meeting in Colorado State University that was organized by Professor Diana Wall. Sadly, we just lost her last month. And I will argue that a lot of policy things here is driven by her leadership. So she invited 20 of us to come together in Colorado to think about how we can bring policymakers' attention on this. And that leads to the productions of this Global Soil Biodiversity Atlas in 2016. That atlas highlighted the importance of soil biodiversity. These publications then encourage the CBD, the Convention of Biodiversity of Biological Diversity of United Nations, and the United Nations FAO to formally ask us to do a formal assessment of soil biodiversity. That was published in 2020, in which we not only assess the biodiversity, we also identify the threat and the steps that is needed to mitigate that threat. The recommendation was then adopted at the Montreal meetings in COP15 meeting by United Nations. 126 countries signed in, including Australia. United Nations then delegated that back to CVD for the monitoring. CBD delegated back to the FAO NetSol, International Network of Soil Biodiversity. At this moment, I chair that NetSol, and believe me, we're just tearing our hair. What should we measure? Not because science is not known. We very well know what we want to measure. The problem is the inequity in infrastructures and lack of expertise. I just give you an example, the sequencing we take granted here in the African continent, and particularly in sub-Saharan Africa, there is 2 countries that have sequencing facilities. So they don't have a facility to measure, they don't have expertise to measure, and it is a global problem. You can't solve this problem in Australia and United Nations. It's a global problem, it needs a global solution. So the global governments need to come together and address this inequity so that we can do the proper assessment of the soil biodiversity. One thing I haven't talked today about the technical advancements in this area because of lack of time. But what I do believe that a system-based approach is needed that integrated advancements in the technical advancements. A strong policy framework. We have some policy framework. I believe it's weak. It needed to be tweaked and make it stronger. We need investments. We just talked about that. And the societal education literacy is critical to advance these things. I will finish my presentation in saying that the Prescott's legacy is transgenerational. You have seen some of the things, the mapping things we do. Almost everybody in our group and globally, the mapping is the way to go particularly for the conservation policy. So thank you very much for the Prescotts for showing us the pathway, and thank you very much for listening to us. Thank you very much.
Brajesh, thank you very much for a really great talk and an eye-opener for us all. We can hear we will have time for questions at the end of the session. But I would like to now introduce our second speaker, Dr. Zefang Shen. Zefang earned his PhD in mechanical engineering in 2020 from Curtin University, where he developed wearable robots for rehabilitation. And since 2019, he has worked with the Soil and Landscape Science Group at Curtin University to develop machine learning research and engineering solutions in soil science. To hear more, please welcome Zefang.
Good evening, everyone. First of all, I would like to thank Australian Academic Science for this for the invitation and this opportunity. It's really a great honor to be here and sharing some of my experience developing artificial intelligence for soil science in my last 5 years. I'm an earlier career researcher with the Soil and Landscape Science group from Curtin, and we will share some of my studies on artificial intelligence for soil science. So first of all, what is artificial intelligence? It is a very general concept that describes the simulation of human intelligence with computer systems. Machine learning is a sub-concept that falls under artificial intelligence, which is more practical. They are computer algorithms that can learn from data from experience. And deep learning is the state-of-the-art artificial intelligence methods that has an artificial neural network architecture. They have multiple layers to learn more and more complex relationship in the data. We have seen many applications of AI in the last decades, I would say. I mean, one of the most important example is ChatGPT. I reckon everyone here should have tried out this tool, or at least heard of this tool. I mean, it also helped me to produce the text here explaining those concepts. So, yeah. Of course, there are many other applications, virtual assistants, autonomous driving vehicles, and some systems which can help people with programming. And of course, we can use AI for soil science. Here are just examples. We can use AI to develop systems and models to predict the soil properties for soil analysis. And also we can use machine learning to make maps of soil properties on large scales. Of course, we can also use machine learning to model soil carbon cycle to make future predictions or to help us to understand the process of the carbon cycles. Professor Prescott arrived in Australia in 1924, and he started to establish some accurate chemical and physical methods of soil analysis. And 100 years later, in 2024, we have some new tools. That's spectroscopy with machine learning. Spectroscopy studies the interaction of electromagnetic waves, which are basically lights, between matters. They carry the fundamental information about the constitutional structure of the material, and machine learning can be used to learn the relationship between the spectral signals and the soil properties. And those machine learning can help us to analyze the different soil properties. Here is an example of a soil spectrum. Usually we use the spectra in the visible and infrared range to predict different soil properties. So we can see here different spectral features can be related to different soil properties. A single spectrum contains the information that we can use to infer many kinds of soil properties. And how we can do this? That's through machine learning. To develop machine learning for soil spectroscopy, first we need to have a soil data set, which consists of soil spectra, of course, and also corresponding soil properties. And then we can divide this data set into a training set and a validation set. we can train our model on the training set and validate its performance on the validation set. Then we see if the model is accurate. If it's not, we go back and adjust the parameter of the model until we reach the plateau of the accuracy. And then we can use this model to predict on unknown data. But developing machine learning for soil spectroscopy is not easy. Here are some challenges we faced in the last few years. So for machine learning to work, we need to tune a lot of parameters, a lot of combinations of those parameters to find the best model with the best accuracy. This process is very complex and time-consuming if the model is complex. Can we automate the whole process? We only provide the machine learning with the raw data, and automatically it will give us the best model with the best accuracy. So this is the first challenge. Another problem with spectroscopy modeling is that we have a very large global soil spectral library. We can develop a machine learning model on that, but when we predict on some soil data collected from a local field or farm, in many cases, it's not going to work. And this is the localization problem. Of course, machine learning has long been criticized as black boxes. There's lots of complex computation happening inside. It's very difficult for our human to understand what actually happens inside. So that's a challenge for interpretation. Here we touch on the first challenge of automation. Conventionally, to find the best machine learning model, people do research, which basically evaluates all the possible combination of those hyperparameters and choose for the best one. Or it could be done through random search by randomly sample some hyperparameter configurations and evaluate all of them. Here is an example of using research. So if we use very simple statistical or machine learning models, the number of evaluations are not that many. It's okay, but if we use a more modern but more complex model, it can take like 10 to the power of 31 number of evaluations. This would not be possible for the computers we have today. So we have to come up with smarter strategies for the hyperparameter search. And the solution we propose here is the Bayesian optimization. This kind of methods can use the information from the historical search of hyperparameters to inform the next search. In such a way, the search of the hyperparameters is more guided and is more likely to lead to better models. And we apply these methods to automatically develop a CNN on a soil spectral library. So on the left here is like graph for CNN. This is the input spectra, and this is the convolution layer. Basically, this convolution layer scans the whole spectra with a small window and extract useful features from the input spectrum. And these features are then processed by those fully connected layers to make the final prediction of soil properties. Here we simply describe how these optimization-based methods can be applied to automate the development of this CNN model. First, the optimization proposed a promising hyperparameter configuration. Then we develop a model and evaluate its performance. And we repeat this process until stopping criteria is reached. And in such a way, we can have the optimal set of hyperparameters. And these parameters can lead to an accurate model. Here is some results on a CNN we developed on the European Soil Spectral Library to estimate soil organic carbon. So we can see the optimization-based methods converged quickly. It only takes less than 100 trials, and it is more accurate than random search. And basically, with these optimization-based methods, we can automate the whole process of developing machine learning for soil spectroscopy modeling. We don't need to care about too much about Hubble band tuning. We only need to provide the raw data to the model, and the process can automatically discover the best model with the best accuracy. And here on the right, we show the prediction of the best models here. Yeah, another problem with soil spectral modeling is the localization. Let's say we have a very large soil spectral library. Of course, we can develop machine learning. And the problem is when we use this machine learning model to predict on some more homogeneous local data, in many cases, the prediction is not going to be accurate. So we need to develop some methods that to localize this kind of modeling to help improve the prediction on the local spectra. But if we look at this localization problem from a perspective of machine learning, this problem is a transfer learning problem. In the transfer learning, we usually have a source domain and we have a target domain. The aim of transfer learning is to improve the modeling for the target domain by transferring some useful information from the source domain. Those kind of information can take different forms. It could be, for example, samples from the soil spectral library. It could be some representations that have been learned by the machine learning model trained on this large-scale library. It could also be the parameters of those machine learning models. Here we show how we can use transfer learning to help with the modeling of organic carbon at 3 local sites. For the libraries, we use 1 global soil spectral library. We use 3 country-scale soil spectral library. And here in this map, we show the location of those samples in the library and location of the local sites. Here are some of the spectra from the local data. For the modeling, we first developed the local modeling using the local data as a benchmark, and we want to have transfer learning that improves the accuracy of the local modeling. We transfer samples from the libraries by selecting some samples from the global library and combine with the local data, and then we do the modeling. We also test transferring of representations. We first develop models on the global library, and then we retrain the model on the local data, see if it helps with the modeling. And we also tested combining those two approach. That's transfer learning of both samples and the representations. Here are the results. This axis shows the improvement of the accuracy over the local modeling. So the 0 line here represents the local modeling, and we want to have improvement above 0. We could see that with the global soil spectral library and with transfer learning of samples, it improved the accuracy for all the 3 local sites with an average of 25.8%. Other transfer learning methods didn't show consistent improvements for all the local sites. So this transfer learning of samples with the global soil spectral library could be an effective method for localizing soil spectroscopy modeling. The last challenge we address is the interpretation of machine learning models. Generally, when those machine learning models they become more and more complex, they are able to learn complex relationships in the data set. But at the same time, they become much more difficult to understand because there's lots of computation happening inside. It's almost impossible for our human to understand. So explainable artificial intelligence are like tools and the methods that help us to open those black boxes and helps to understand why they make certain predictions. And the one example is the shape values. It is a model agnostic methods which can be applied on different machine learning models to understand what are the important factors affecting the prediction of the machine learning models. We applied these methods to understand the spectroscopy modeling of soil organic carbon and its fractions. we have 397 samples across Australia, and we measured particulate organic carbon and mineral-associated organic carbon in 2 size fractions. And we also collected MR spectra on the whole soils, and we modeled the SOC and these 2 fractions with the optimized CN, which I described about, before, and also with compositional transformation. This compositional transformation makes sure POC and MOC summarize to SOC as one. Here are the feature importance we derived with those sharp values. If we look at the SOC here, for example, these 2 peaks are related to the CH in the organic compounds, so they can directly inform the carbon in soil. These 2 peaks are for the OH in the clay minerals. These are also important because much of the carbon is bonded to the surface of the clay minerals. If we know how much clay mineral in the soil, it also can help us to predict soil organic carbon. The importance for POC and MOC here are a bit different to that of SOC. There are 2 important observations here. One is that the feature importance of POC and MOC, they are identical. So it makes sense to me because in the modeling we use compositional transformation, which makes sure POC and MOC sum up to 1. That means an increase in MOC will cause the equivalent change, reduction of in POC. So basically, even though they are predicted separately, but the modeling is basically one thing. So that's why the feature importance here are almost the same. For the prediction of POC and MOC, in addition to the peaks related to carbon, related to clay minerals, and also we have some additional peaks here. These are related to the OH in the organic compounds. That's because those functional groups help carbon to bind to the clay minerals, which are more prominent in the MOC fraction. Yeah, in this case, if we can predict MOC fraction accurately, and of course we can predict POC accurately because they sum up to 1. So yeah, generally with this kind of explainable AI with Shapley values, we can have some understanding how the models use different features, spectral features to make the prediction. And this could help us to have more confidence in our model because it does use some relevant information to make the final predictions. So yeah, so for up to now, we have seen how AI can be used and how we address those challenges for soil analysis. Of course, for future research of AI in soil science, there's more we could do. First, obviously, we definitely need to explore more of AI for soil science because AI is a very active research field. Every so often, there's a breakthrough. There are some new methods, and it's better. There's simply value for us to explore those methods, see if they can help us with the problems in soil science. And it is also important to have our own solutions, customized AI solutions for soil science, because many of the methods are developed on a different data set for a different problem. They might not fit our cases in soil science. So it would be better to develop our own solutions for soil science. And yes, also with AI, we can develop accurate models making good predictions. When combined with XAI, it is also possible for knowledge discovery. Also, in the last decade, obviously, we have seen so many applications of AI in many other different fields. I think this is also happening in soil science. So I reckon in the next decade or so, we could see some practical applications powered by artificial intelligence. Yeah, some reference for this presentation. I would like to acknowledge my group for their support in terms of the data and computing. Thank you.
Thank you very much for a fascinating talk, and it's wonderful to see an application of AI. We can now have questions for both our speakers. If you want to ask a question, please raise your hand, and a mic runner will come to you. So you can, yeah, there's one question up there. If you're watching online, you can submit your questions via the QR code, and we will also look at those.
Thank you for your talks. Just a localised question. Which do you consider to be the best Australian soils as far as microbiome, etc. goes?
Can you perhaps say it one more time, the question?
Thank you for your talks. More localised question for Australia. Which Australian soils do you consider to be the best as far as the microbiome, etc. goes?
Thank you very much. The questions, I wouldn't characterize the type of soils or the locations. I guess if you're just looking for the diversity, where you have higher heterogeneity in the organic matter, you probably have a higher biodiversity. But health is not just biodiversity. It's increased, so the biodiversity is a number of species, but also how heterogeneous those diversity are. So it depends upon how you look at it. But if you're looking for the diversity, you're probably looking more, in my opinion, just as assumptions. There is a data. If I need to go back and look into that, I can tell you. But just on the assumptions of the factors that drive microbial diversity, I will argue probably you will see more in the northern part of Australia, Queensland, and other part where you have a more rainfall. Compare, if you, for example, comparing that to the Western Australia, where we have sandy soils and less rainfall, if that answers your question.
Do we have a question online? Yeah.
We do. I've got a question here from Ian in Darwin for Zefang. You mentioned that some artificial intelligence is beyond human understanding, and we must focus on explainable AI. Is our own comprehension a genuine limitation on how much we can and will get from AI tools and methods?
I think the XAI or explainable AI is still like a going on research field. Although we have some methods to understand those models, for example, the one I showed in my talk, the Shapley values. But it's a method that looks at the overall performance of the model. But what happens inside of those, for example, the convolutional neural networks, I think this kind of methods is not feasible. Of course, there are methods that tailored, for example, for those neural networks that help us to actually look at those features which are learned from data inside of those models. I think those methods could be also useful, but I have not seen so far that people using those methods to understand the models, for example, for soil spectroscopy. But I do foresee there are more methods from other fields developed, and there will be more methods, developed in soil science to address those problems. And that's why also I think it's important to have our customized AI for soil science, because many methods developed in other fields, it may not work well for the problem we have in soil science.
Okay, there's a question over there.
Thank you for two very, very nice talks. You've described a trajectory which we are on and our dependency on soils. That trajectory is not very attractive and looks like it's going to get worse. Many of the things you've talked about address how we can describe that trajectory with increasingly sophisticated methods. But I'm wondering whether we are actually doomed to follow that trajectory, or whether you can jump off and look at alternative ways of supporting at least human life through perhaps factories or the marine environment, as opposed to this dependency on soils. Could you comment on that?
I'm happy to answer that question. So I think there's no substitute for the healthy soil, in my opinion. Obviously, we as a human society and human endeavors, we look for every aspect of the solutions. And I'm not saying there's no solutions, other alternative solutions from the marine systems. And what will the technology looks like in 200, 300, 400 years from now on is different. But in the short period of time, and I'm talking about decades, centuries, we will live on the terrestrial ecosystems. We are terrestrial animals. And so we will live on the terrestrial ecosystems. We will get most of our food from the soil. Increasingly, there is different methods of food productions for vertical farming, the protected cropping, and they all will contribute. But the majority of the calorie intake in foreseeable features in future, in my opinion, will come from the soils. So the maintaining healthy soils is a critical component of our survival and our sustainability. That does not mean we should not look for the marine systems. We are looking for the space. How are we going to a space for the human benefits? So there are the things that we can do, and we should look for all the options. But in foreseeable future, the healthy soils will remain a cornerstone for the human sustainability in a human society. That's my opinion.
Here's a question.
Hello, I'm not a scientist, but I'm very interested in knowing whether you are looking into the impact of chemicals on soil health, pesticides, herbicides, fertilizers.
Of course we do. As we all are scientists, the focus of today's presentations, probably you have noticed that I haven't really focused on the production side of things, the agriculture productions. It was deliberate because I will argue that probably people do understand a little more about how important the soil is for food productions. The other aspects gets ignored as a part of that. We do look at that, and there is a lot of research to look at that. It is about sustainability. I am one of the persons who believe the current farming systems needs to improve, but we can't replace them, at least foreseeable future. I'm talking about several decades. So we can't have organic farming to feed the growing populations of the entire world. That might happen in 20 years' time, 50, 100 years' time, but not in the foreseeable future. So particularly the nitrogen and phosphorus fertilizers, we will be using that for a foreseeable future. The impact, as long as we make that sustainable, as long as we use them cautiously and judiciously, I think we are okay. And we should not forget that by farming, we mine minerals from the soils. So if you're not putting phosphorus, nitrogen is replaceable through the biological processes. For example, phosphorus is finite. It is mining every time we harvest. So we need to put it them in some way, one way or other way, through the organic inputs or through the inorganic inputs. So fertilizers treatments, in my opinion, will remain a component and a critical component of the farming for foreseeable future. It is about adjusting and using appropriately that makes it sustainable. Pesticide is a very different thing. We know it have a significant negative impact of the pesticides, not just on the soil health, but all other aspects of the human health, the water health, and everything else goes with it. And so we need to look into that in more details, honestly. And in fact, the efficacy of, particularly, for example, I always give the example of disease because I work with the disease. Most of the fungicides we use in the farms, particularly the soil-borne fungicide, does not work at all. Pythium, Phytophthora, Verticillium, Fusarium, these fungicides does not work at all. So we are probably wasting our resource on some level and polluting our environment. So the alternative resources to managing those diseases is better options, using the plant variety, using the microbial inoculants, using the biocontrol is a better option. And there is direction in that directions to look into that matters. Thank you.
Thank you. Perhaps we can have an online question.
I've got another question here, this one for Zefang. How accurate is the application of AI in measuring the properties of soil, and how would you describe the potential for its future use?
I think that depends on what kind of sensing data do you use, and also that depends on the models you use. And for the soil organic carbon, we use Caemmerer spectra to predict the carbons with R squares above 0.9, which is pretty accurate. That really depends on the sensing quality of the signal, and also if the spectra does contain some information related to the soil property. We do have some soil properties that cannot be predicted well with those kind of spectra. So in that sense, probably using whatever machine learning will not going to work, because the spectra itself does not contain information related to those soil properties. So overall, so if you are going to developing some machine intelligence, machine learning to predict for the soil properties, you need to make sure your sensing data does contain the information that relates to those soil properties, and try to use a good model that might be based on a bit of trial and error, see which one works best, and then try to build a proper data set that works for your problem. So yeah.
I've got a question up there, perhaps.
Thank you both for wonderful talks. I was fascinated by the fact that human pathogens may be found more often in particular soil types. So a question for Professor Singh: do you know if there is any correlation between particular soil-borne human pathogens and altered redox states? Just coming from a biochemical sense, in that, concentrations of iron in the human body can exacerbate certain opportunistic infections. Is there a similar correlation in soils?
The honest answer is that I do not know. The analysis we recently did on the global soils, we do see some correlations with the availability of ferrous iron in the soil. But the specific questions about the role it plays, I don't think we have knowledge. We actually see some correlations with the ferrous ions in the soils and the pathogens' dominance or lack of dominance. But I don't think I have seen, or in fact, I've investigated the role in the biochemical processes.
I will have one from the online audience next.
Sure, this is also for Zefang from the online audience. John in Canberra asks, do you or other researchers have experience with AI models to estimate soil organic carbon sequestration potential and actual increments?
That's a very great question. Actually, we have just published one paper early this year that studies the carbon sequestration potential across Australia. And we have one PhD student exactly working on this project to predict the potential of carbon sequestration with some of the spectral data sets. Yeah.
I think there was a question in the audience there.
Hi, thanks for the really great talks. I have a question around the machine learning bit. You mentioned that you automate how to choose the best model for the data, but I just wanted to understand how do you automate that process? Because I can imagine in the case of, let's say, deep neural networks, even though you can automate the selection of hyperparameters and all those variables, you would still need a starting point to at least select the kind of layers you need to put in the neural network. So I just want to understand, how do you decide like how many convolutional layers do you need, or pooling or activation layers? Because if you automate the entire thing starting from, let's say, 100 combinations of these different deep neural networks, I can imagine there will be multiple combinations giving the same results or conflicting results. So do you look at the data and select a structure? How do you go about that process?
Thanks for the question. You must be a very good machine learning practitioner. Yes, it's a complex problem. So because if you know convolutional neural network, you probably know there's lots of parameters to tune, and the methods we used, we first defined an optimization problem, and the target is to reduce the RMC score, which is score to measure the accuracy, and we first randomly sampled some hyperparameter configurations to establish a history of hyperparameter search, and then from this history we can propose some new hyperparameter configurations. And how we define those configurations, we develop an representation of CNN. For example, we divide CNN into different building blocks. We have a convolutional block, we have fully connected block, and for each of those blocks, we have some parameters, and those parameters are optimized through the optimization. Once we finish the optimization problem, and it will come up with the best parameters that describes a CNN, in that case, we will have the final CNN. And yes, in that case, we can determine how many convolution layers in the CNN, how many fully connected in the CNN, and what's like the filter size in the CNN, for example, those kind of parameters. Yep.
Well, thank you all for your great questions, but I'm afraid that's all we've got time for tonight. And a huge thank you to both Zefang and Gerard. They're really fascinating talks. And, so we appreciate you sharing your time and your knowledge with us. And thank you to my co-conveners of the series, Oliver and Raffaella. And a final thank you to all of you for joining us tonight. If you've purchased a series pass, we will see you again for the next installment on Tuesday, the 11th of June. And if you would like to attend and have not yet purchased a ticket, please visit the Academy website for more information. Thank you and good night.